Okay, so it's a great honor to be here and to present this introduction. So I will try to give some common knowledge that will be useful for the other sessions. And it is supposed to be a little bit interactive. So please, if you have any questions or comments, just interrupt. We have a lot of time this morning to discuss. So, okay, so are you ready? Yes. Thank you. Anyway, so there will be some examples. They are coded in either MuPPL or BioPPL, which are programming languages that have been designed for teaching probabilistic programming. So you can go on this website and test them if you want. Okay, so the first message is that a probabilistic program is a random variable, and we will go through examples to understand what it means. Okay, so what is this program doing? So there are two versions because some of the sessions will use an imperative programming language and some other will use a functional programming language. So you can choose which you want. Okay, so let's look at this DICE program. What is it doing? Okay, it is supposed to be interactive. Yes. Okay, so if I run this program, exactly, I will simulate a random variable which throws two dice and compute the sum of the outcomes. So to describe this random variable, I need to describe the experiment which I simulate. So the experiment here is the throw of two independent dice. And when I describe a random variable, I need a probabilistic space, which is described with a universe. The universe is the set of potential samples. So here, my universe is just the Cartesian product of 1 to 6 with 1 to 6. And the probability that is associated to each sample is the joint distribution. So if I take A and B, I will get if I take A equal 3 and B equals 4, I will get that with probability 1/36. Okay, so now this is not enough to describe a random variable. A random variable takes samples and outputs some outcome, and here it's the sum of the samples. Okay? So DICE is a random variable which goes from the space, the universe, plus the probability, and gives an outcome. Here it's an integer. So to A, B, I will output A plus B with probability 1/36. Okay. I am not interested in simulating this random variable. I am interested in its law, in its probability distribution, and to describe it, I can use enumeration tree. So this is the sampling tree, and how is it designed? Here you have, first you sample A, and you will get the value 1, for instance, with probability 1/6, 2, 3, etc. Then you sample B, and you will get another outcome, another sample with probability 1/6. And to this trace, 1A is 1, B is 3, I will get the outcome in green, 1 plus 3, 4, with probability 1/36. So here I have all the possible execution of my simulating this random variable. Okay? And it's enough to describe its law. How do I get this law? I just have to sum to know what is the semantic of DICE. The semantic of DICE is the probability that I get an outcome. So what I am interested in is the law associated to the random variable simulated by DICE. So the probability that DICE produce an integer k. So what is this probability? I just have to sum over all the samples, A, B, such that A plus B is equal to k. So here you have the Dirac, delta A plus BK, it's equal to 1 when k is equal to A plus B, and 0 otherwise. Okay? I'm also interested in some characteristic of this probabilistic law. So for instance, the expected value, which is described as the probability that dice output k multiplied by k, and I take the sum. Okay, and from this, I can also draw the histogram, so the probabilistic mass function, which is associated to this random variable. Okay, so let's make a try if it's really working. So this is my my program here. I can put it a little bit bigger, and I can run it. Okay, so what is it doing? Here, I'm using an algorithm, enumeration, which is an inference algorithm that will compute the law which is associated to this programming, simulating my random variable. What is it doing? It will just go through the enumeration tree and gather all the elements to get this histogram. Okay, so now that you have understood, that's your turn. So what is this program doing? So because it is simulating a random variable, what you need to do is to understand what is the universe where the experiments are taken, what is the outcome of the random variable, and what is the law that is associated. Okay, so yeah? Exactly. So it is a random walking over the integer. And what is the universe? What are the samples? Yeah?
Depends on the n given, there is a threefold n inputs of, I guess, floats between 0 and 1. That's probably they could normally just 0 and 1.
Okay, so Bernoulli is a random variable that will output true or false.
Okay.
Okay, so your proposal is? So first of all, it is a parameterized random variable. So what we get is a parameterized distribution. And the universe is given n. What I will do is I flip n coins. So the universe is the potential samples that I can get that are sequences of Boolean, sequences of length n. Okay, and what is the probability distribution of my associated to my probabilistic space? Well, I will get the joint distribution over n copies, independent and identically distributed. So n copies of my coin, and to each sequence of n Booleans, I will have associated the probability 1/2 to the n. Okay? So I need two things. I need the universe, but I also need to compute the outcome. So what is the outcome? I just have to count how many times I get true, and I will get the output by taking the sum. Okay, so what is on the left? It is one experiment, one execution of this program, one simulation, and it is a sampling trace. So now I can compute the sampling tree that is associated in order to compute the law. So at each step, I have n steps, and I need to choose if I take true or false, with probability 1/2, and I do that n times. So my tree is becoming bigger and bigger. Okay. So, and this trace is corresponding to, so I go true, let me exchange this. False, true. So I go 2 twice, and then 4 times here, and then twice, 1, and twice again. Okay? So this random walk is one sampling trace. Okay. So now I can compute the probabilistic law that is associated to it. How can I do that? I can just run my program. Random walk. And I get this histogram. Okay, so I'm also interested in the expected value. So the expected value is computing with this sum and with the standard deviation. We are not always interested in all the probabilistic distribution, but sometimes we only need to consider the expected value or the mean, the standard deviation. Okay. Another example. So here I have 2 different examples. So let's look at the left. What is it doing? Yes? Exactly. So it does the coin and continue until it gets a false. Right? What is the universe?
Bounded sequences of n sequences
Okay, so now my enumeration tree, what is the shape of my enumeration tree? Yes, it's a little bit like a combo. Okay, so but it is infinite in depth and width. Okay, so it's starting to be difficult to enumerate all the traces to get the law, to compute the law. Okay, so now on the left-hand side, what is it doing? Yes?
It simulates a fair point by repeatedly sampling a biased coin where you put it twice, and there's a rejection sampler where it repeats if the 2 biased coins return the same.
There's no rejection sampler here.
I think there's a whisper right instead of left.
Oh, no, it's not.
Sorry?
You're describing the right hand side.
Oh.
That's not the left hand side.
No, I'm describing the right-hand side. No, I'm just saying that I didn't decide what will be the inference algorithm. The inference algorithm is an algorithm that allows me to turn this simulating program into a probabilistic distribution. Okay, so you are just speaking of rejection sampling, but I didn't decide what will happen here.
But it's recursive, isn't it?
It's recursive, yes.
Yeah, so it repeats, it attempts to keep on, okay, maybe the term is wrong, but it repeats until you get 2 samples which are different, and then it returns the first one.
Yes, exactly. But I agree it's the principle of rejection. Yeah. Okay. So it is a recursive program here. I can do whatever I want. Now I'm embedded in expressive programming language, so I can extend my probabilistic programming language with many constructions. But I need to give a semantics, a meaning to this construction. Okay, so what is the universe associated to the right-hand side program? What are the samples? So my experiment is to repeatedly toss 2 coins. Okay, so any idea? Yes?
It's not an idea, it's a question.
Yeah.
What are the two arguments? What is probability?
Okay, so prob is a detail of implementation because we are in presence of effects, probabilistic effects, and so we need a state to memorize what are the current effects. And if you want to know more, just ask Guillaume. The other argument is the probability distribution that you started with. So it's a Boolean distribution, and what you are, we can assume it's a Boolean distribution. So Boolean distribution, you have only Bernoullis, and that might be a bias coin, and you want to recover exactly a fair coin. So let's try to see if we can get a fair coin. Up. So here in OCaml, I don't have the visualization, but you can see the mean of this Boolean distribution, and it's 0.5. And I can change my parameters here. Here we don't care. And it's again 0.5. Whatever the parameter p I put here, what I get is a fair coin. Okay? So, what are the universe that are associated to these random variables? So for stopping time, I sample IID copies of the distribution D with support in X. And the universe then is just sequences of elements of X. And the samples are taken in the joint distribution. Okay? So the outcome will be n if I have the trace, the sampling trace, which is n times true and 1 time false, followed by 1 time false. For the right-hand side, I also sample IID copies. IID means independent and identically distributed. That's the same random variable that is copied. And the universe is sequences of pairs of Booleans, one for A, one for B. And because it's recursive, I will repeatedly sample twice in my distribution D. And the outcome will be true after I have sequences of pairs of the same samples, and then true, false, or false, true. Okay? So I'm not interested only in the universe and the probabilistic space, but also in the probability distribution. And for stopping time, I can just run it. And I get this histogram. I can change the distribution in which I am sampling, and I get another histogram. All right? Yes?
So the universe here is only finite sequences of arbitrary length, or
yeah.
Is there also the infinite sequence in the universe?
There are many. There are many ways of representing a random variable, so you can take both. But the infinite sequences will have probability 0 of appearing. We can prove that if if the bias is not 0 or 1. Okay. Any other questions about that? Okay. And for the random line, as I tested, it's a random variable, Boolean random variable, whose mean is always 0.5, or approximately. Why approximately? Because as we said, the enumeration tree now is infinite, is not the depth and the width of the enumeration tree is not bounded. So I cannot perform the enumeration, enumerating all the traces, gathering the outcome, and computing the probability. Okay, I need another way to compute this probabilistic law, its characteristic, its probability distribution, and I need approximate inference. Okay, so we will use as a reference inference algorithm importance sampling. Importance sampling, it is an approximate inference algorithm which will take a random variable and will repeatedly simulate it. If the probabilistic program has no effect, running it twice will give you the simulation of two independent and identically distributed random variables. My two copies do not interact because there is no effect, no memorized state. Its executions are independent and follow the same law. So now I can use the law of large numbers. And the law of large number tells me that the experimental mean approximates the expected value. Okay, so the sum, the average, x1 plus xn over n, will approximate the expected value. And if I take g such that the expected value of g of x is finite, then the average, the experimental mean, will g of x1 plus g of xn over n will give you an approximation of the expected value of g of x. Okay, that's just the law of large number. So now the importance sampling or the Monte Carlo simulation will just, you take your program, you run it n times, you compute the average, and you get a good or not so good approximation of your expected value. And from that, you can compute histograms by changing g. Why? Because for a random variable, the number of times the outcome of the random variable xi, the i's outcome, will approximate the characteristic function of being equal to x. And this is the probability that x is equal to x. Okay? So if I want to know what is the probability that the outcome of my dice is 7, then I can just count how many, throw my dice 1,000th of time, count how many times I have 7, and just compute the frequency. Okay? And that's what I use, for instance, for stopping time. I use importance sampling with 10,000 particles. That means that I simulate my program 10,000th of time, and I get a good approximation of the probability distribution. Okay, so what we get now is we have understood that a probabilistic program is a random variable, and we have taken samples in different probability distribution, uniform, Bernoulli, so coins that can be fair or biased, and categorical, empirical distributions, and so on. The outputs are discrete, so they are taken in Boolean or integers, and that's why they are discrete random variable. And we are interested in computing their law. We can do that, compute it by exact inference if the trace tree is finite and the enumerating tree is finite. And if not, we need to use approximate inference algorithm like importance sampling, which is using Monte Carlo simulation. Okay? So if you have no question, you are in a good place to start the week. Do you have questions? No? Okay. But we need to prove some properties on our program because we are in the programming language community, so we love to transform programs, compile them, and do many proof on them. So we will need operational semantics, denotational semantics, verification techniques and equivalence of programs. So that's the subject of the course, courses this week, but we need some introduction before moving to the next sections. Okay, so let's start with probabilistic semantics. But first, what is semantics? There are two main semantics: the operational semantics, which represents programs as transition system, whose configurations are the states of an abstract machine that can be a Turing machine, a Krivin machine, a push-down automata, or whatever is your favorite operational semantics, or it can even be a rewriting system on terms. If you like that, you can go and read this article that I like a lot, and by Peter Lanza. And the second stream of semantics is denotational semantics, where program denotes or represent functions that act on values or on memory states. Okay, and you can also read this article by Scott and Strachey, which introduced the denotational semantics. Okay, so here we are interested in probabilistic semantics, and it was, I think, introduced by Dexter Cozen in the 80s. This article, there is everything in it. It's very nice. So it's a good advice to read it. And probabilistic programs, they denote or describe statistical models. That's just what we've seen. And we want to compute either exactly or approximately the characteristics of the random variable that is simulated by the program. And the formal methods make possible to prove that a probabilistic program describes the correct statistical model, which is not that easy when you run the program or when you try to compute approximately its the associated probability distribution. And we also want to prove that the implementation of an inference algorithm is correct. That's not easy also to do. And we also want to prove that program transformations are correct. Sometimes, in some situation, you first need to transform your program before performing the inference, and you want to prove that you do not change the probability distribution by transforming your program. And for that, we use semantics. Or we can use semantics. You don't have to. You can use other tools also. Okay, so we will have a look at probabilistic semantics. Two kinds of probabilistic semantics, for imperative programs and for functional programs. Okay, so this is the syntax of simplified mu-PPL. Okay, so I have types which are discrete here, and I have some expression, the constant. The constants may be integers or booleans or probability distribution, like a Bernoulli. I have pairs, I have operations, and I have also statements in the S. I can do nothing, I can do an assignment, as usual. And I have this construction, which is first sampling the probability distribution represented by the expression E, and then assign to X the outcome of this sampling. And I can define first order functions, and I can use them. Right. Here, the only distribution that we will consider are bias coin. But here I write Bernoulli of Pei, but you will see as many notations as you want. So a coin is usually a fair Bernoulli of 0.5. Flip P means that you will toss a coin which is biased with bias P. And the plus P here means that you first toss your coin, your bias coin, and then according to the result, you decide to do E or E prime. Okay, so many notations depending on whatever probabilistic language you want to study, but it's always the same thing. Okay, so just a little break on discrete random variable, what we have seen till now. So we have seen that a random variable is a function from the universe to the outcome. So here it's discrete if it takes a countable number of values. So here I put R, but it could be Booleans, it could be integer, whatever the output type. And we are interested in the probabilistic mass function, which is for a discrete random variable, it's a function f, which is computing the probability that the random variable outputs x. So it's the probability of all the sampling traces such that evaluating my random variable x on this trace will give me x. That's the probabilistic mass function. Okay. The mean is given by taking the mean scored by the probability of getting an output. And I can also compute the mean or the expected value of a function applied to x. That means that I will first sample and then apply my function and take the average over weighted by the probability distribution. Right. Now we know what theoretically is a random variable. How can I represent it in a probabilistic program? Well, I will not give the whole. I can give the whole. Sorry, let's do it again. So I first need to know what is the support. So what is the output values, because I will sample in that, and I need often the support. I need to encode the mass function, and often I will just put them in also to represent my distribution, so that when I need it, I don't have to compute this expected value. I also need a way to sample this random variable, and so a sampling operator. So what I'm interested in is the different probability distributions that I will use. So I have this Bernoulli, a Bayes coin. I have binomial. A binomial, you know what it is doing? You take a Bayes coin and you throw it, you toss it n times, and you look at how many times you get true. An empirical or a uniform over a list of outcome. Well, it's getting you any element of the list with probability 1 over the length of the list. And finally, a categorical, it's given by a list of outcomes with their probability. So for each possible outcome, you give the probability of getting this outcome. That's the only probability distribution that we will consider. And if you were awake, you have remarked that when I perform important sampling here, what I get is a categorical distribution. So it's an approximation of my probabilistic law by a list of samples together with the probability of getting these samples. So this inference algorithm is computing a categorical law which is approximating the law that I am interested in. Okay, so now that we know everything on random variables, discrete random variables, we can give the semantics of the statements. First, the semantics of the expressions. There is no random or probabilistic construct here, so it's just this deterministic. It's the usual deterministic semantics that you know. But if I want to give a sampling semantics, I need so the sampling semantics is the enumeration tree. You need to have this representation in mind. So to each sample, I will associate a key or a name, like here. So for the first sample, I have the name A, and for the second sample, I have the name B. It's just to remember which one is what, is which. Okay. So now to each sample I have a key, a uniquely defined key. And I want to define a sampling trace. So a sampling trace, or a trace of samplings, is a map that will associate to each key a sample in the support of the sample distribution. And we will call omega, I use omega like the universe, omega to be the set of sampling traces. Okay? And now I can give the semantics of a statement. What it will do? It will take the environment, what are the variables that have been defined. It will take a sampling trace, and it will take a current probability, a real, and it will produce a new environment, and a new sampling trace, and a new probability distribution. And the meaning is as follows. If performing S over the environment, the sampling trace, and the probability give me gamma prime, sigma prime, and rho prime, that means that the statement S may have consumed samples from the sampling trace sigma with induced probability P. It will have used values of the variables that are stored in the environment gamma, and it will generate a new trace of the remaining samples, the one that I have not used for now. And the updated probability, so rho prime is P, the probability that I can use this sample, multiplied by the preceding probability rho, and the updated environment gamma prime. Okay? Yes? The induced probability means to each sample you have a probability. If you remember this enumeration tree, which is really small, this enumeration tree, to each sample you have a value and a probability to get this sample. So the induced probability here for A equals 2 is 1/6. Okay? Just a remark on notation, and then I answer your question. So a sampling trace, sometimes it's called entropy, sometimes it's called an oracle, sometimes it's called a probabilistic scheduling, a random database. Each author has his own view on that, but it's always the same idea of the enumeration tree and the traces in this enumeration tree. Yes, what is the question?
Why do we need to consume the samples? Why do we need to update our trace to get rid of these samples?
So it depends on the way you define a semantics, but I had to choose one. And the idea is you start with an infinite sequence of samplings, and you will use the first one to perform the first statement, and then you have the remaining to perform the other statements. Okay? So according to the key of the sample you are performing, you will go into your sampling trace and choose the associated sample. Okay, let's have a look at on an example. So first, just some selected rules. So what's happening with when I perform a sample? So here I sample in a probability distribution of low mu with key k. I start with an environment. So in what is the current memory in which I am evaluating my statements, and I have a sampling trace in which the k is associated with the sample v. And till now, I have produced consumed samples with probability rho. So what I will get is, so now x will take the value v. So my new environment is gamma, where I have added the association between x and v. Sigma prime is just the, it's sigma here. I get rid of this key because I have consumed it, and I update my probability distribution by multiplying by the probability that mu outputs v. Okay. Now, if I want to make a sequence of statements, I will just chain, as usual. And I can also associate to any function, that's a declaration of function, a function that takes the input, the sampling trace, and that outputs the value of the expression E, evaluated in the context after S, and with probability rho. Okay? So, because there are many different definitions, perhaps you can try to define the sampling semantics of dice. Yes, you need a paper, perhaps. Okay, so dice is a declaration. And S, the statement, the main statement is A equals sample of round 16 with name, with key A. B is the same thing but with key B. And the expression is the sum of the two samples, right? So, to associate this function, lambda v, lambda sigma, blah, 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 I first need to evaluate the sampling semantics of my statement, starting with to x, I associate a value v. Well, this program doesn't take any parameter. So to no parameter, I associate the unit. Nothing to do here, so I start with gamma, which is the empty environment. There's nothing here. So now I need a sampling trace. Do you have a proposition for sampling trace? So a sampling trace will associate to each key appearing in my program one sample. Yes? Okay, so for key E, A, sorry, what do you propose? You just have to make a choice. No, I want a real trace. Three? Yes. And I need also a value for key B. Two. That's not probable. Okay, so I have my sampling trace. And now what do I need? I start with probability 1. Okay, so I have two statements here that are sequentially executed. Okay, so I can use the sequence rule. So this S is S1 followed by S2. What do I need to do? First, I need to evaluate S1 with the empty environment, my sampling trace, and probability 1. I love this effect. So what will happen? Oh, okay, so S1 is a sample, so I can use my rule, sample in random 1/6. So what's happening? What is gamma by the end of the day? Okay, so my new gamma is I equal 3. What is my new sampling trace? B gets 2. Yes. What is the probability? 1/6. Okay. So that's gamma prime, sigma prime, rho prime. So let's start for S2. What do I get? I'm sure you know. A is 3, B is 2, and my sampling trace is empty, and my probability is 1/36. Okay, so now I can say that this is gamma second, the empty as sampling trace, and 1/36. Okay, and now I can compute the semantic of dice. So what will be the output? I need to evaluate the expression E, A plus B, in this context, environment, sorry. In this environment, A is 3, B is 2. Okay, so if I have any sigma, it will be sigma A plus sigma B with probability 1/36. Okay? So I think it answers your question, what's happening with this sampling trace. It is consumed along the evaluation of the statement. Okay. Do you have questions about this semantics? Yes?
If I have a program that calls dice twice in a sequence, what's its semantics?
So here, because I want to keep simple, I will choose different names.
Okay, so you can't call dice twice.
If I want to call dice twice, then instead of one sample to each probability distribution, I will have a sequence of samples that I will consume one after one. But here we stay simple. Do you have other questions? Okay, so we have a sampling semantic. Okay, so we have a sampling semantics now. Okay, no, so you will have exercises at home. There are two things to remark here. I just want to compute quickly with you what will be the sampling trace. What does sigma looks like for the left-hand side. So I have a probability distribution D. I can get the output. So first of all, to answer Guillaume's question, what will be the keys? K will be, I can take like whatever string indexed by, let's say, K. Okay, so for the binomial, I think I have no. No, I don't have it. Okay. What will be the sampling trace? So imagine that D is whatever, a Bernoulli. And for K in a range N, I will sample this Bernoulli of P with a different name, like of a string of K. Okay? So what will be the samplings? I don't move. Yes?
So we will have key 0, 1, key n-1.
Yes, one example. So it will be key 0 gets one value, let's say true, key 1 false. Do I really need this microphone? Key n-1 gets whatever value, true or false. Okay, so any sampling trace will have this, this shape. Okay, and each time I perform one such sample, I consume one of this key, this k. Okay, and now for flip sum, what's happening? What will be what it will look like? So I first sample my probability distribution D, and then I compute for k in range n the sum of the same sample. So what does the sampling trace look like? Yes? Yes, just one element, k is true or false. Okay? And then I copy the value to get the sum. Right. Okay, so we have one kind of semantics, the sampling semantics, but there is another kind of semantics, the stochastic semantics. I call that stochastic semantics, but I'm not sure everybody will agree with this terminology, but whatever. So what is a stochastic matrix? A stochastic matrix is a function from to a set x and y. To x and y, it will associate a positive real number, such that for any b, the function from x to r plus is a function, and for any x in x, the function from y to r plus is a probability distribution over y. Okay? So if I fix x, then I get a probability distribution over y. Okay, so what a statement in this semantics, in this stochastic semantics, will be interpreted as a transformer of an environment into a probability distribution of updated environments. So I start from an environment and I want to perform this statement. And what I will get is a probability distribution of the updated environments. Okay, so let's look at our favorite example. I'm sorry, I forgot my two dices are. Okay, so what's happening here? For this statement is assigning to x the output value of sampling E. So it starts with an environment gamma, and it will produce a probability distribution over environment. What is the probability of getting gamma prime? Well, I have to sum over any output value of my probability distribution mu. This is the semantics of E. And I will multiply the probability of getting mu with the fact that the output, the updated environment, is the old environment where I have added the value x associated to where the variable x is associated to v. Okay, so doing this assignment is computing the probability distribution over every possible output variables, where the output, the updated environment, is just gamma plus the new variable, right? Now, the sequence. Well, it looks like the bind of a probabilistic monad. I will sum over all the potential updated environment after S1, and multiply the probabilities that S1 starting from gamma will produce gamma prime with the probabilities that S2 starting from gamma prime will produce gamma second, and I will get the probabilities that the sequence start from gamma and go to gamma second. And I can also compute, associate to any declaration, a function that computes the probability distribution associated to the body of the function. Okay, so that was for the theory. Let's go to the practice. Okay, so I need to give semantics to S1, S2, and what I want to compute is the probability distribution. So the semantic of dice is a function lambda, well, there is no input value. And what is the potential output value? It will be V prime. And I want to compute, given that the input value is V, there is no input value, what is the probability to get the output value V prime? Okay, so V prime is the output value of my dice. What are the, taking the sum of the two dice, what are the possible outputs here? The sum of two dice, it's, yeah? Between 2 and 12. Okay, so that's the output. That's the input. And I want to know what is the probability that starting from the input, I will get whatever value in this set by performing this statement S. Okay? So I need to compute S of the empty environment into gamma of the... Okay, so what are the potential gamma after performing, throwing the two dice? Okay, let's have a look. S1 is, let x equals sample my dice. Okay, I start with the empty environment. I'll have to sum over all potential value of my dice. The probability of getting this value A, and the outcome will be well, what do I have to do? I have to add the value A to my variable A. So let's, too many A. Okay? How many gamma prime do I have in this sum? What are the possibilities? Sorry, my questions were, how many K do I have? If I give you an output, a gamma prime, an updated environment, what are the potential values here? So I do it again. So what is the probability of starting from the empty environment and getting to A is value, let's say, 3. In this sum, because this is equal to 1 if gamma prime is equal to this environment and 0 otherwise, I will have only 1k, which is non-zero. The summand is non-zero, and it will be 1/6 delta A3. So this is delta K3. So K is equal to 3. Okay? So now I can do the same thing starting with S2. So I start with A is 3. And for instance, I want to know the probability of getting B is 2. And I will have to, it will be 1 over 6. So starting from A3 and getting the environment where A is 3 and B is 2 is 1 over 6. Okay, so now I can compute this. And for any gamma of the shape A is something, B is something, I will get probability 1 over 36 by multiplying the two. Okay? So now I know what is K, what is the semantics of S, and I need to compute this kernel. Okay, let's do it. So I sum over all potential E, V, gamma, gamma, V prime, okay. All potential gamma of S starting with the empty environment and getting to gamma, and getting V prime as the output value or the semantics of E in this environment gamma. Okay, so what I can get is A is something, B is something, and the semantics of E will be gamma of A plus gamma of V. So it's equal to, I'm sorry for this. So it's equal to sum over gamma of 1 over 36 multiplied by delta V prime of gamma A plus gamma B. Okay, so what am I doing? I am computing the sum of the probability that V prime is equal to gamma A plus gamma V. I am summing over all A and B such that the sum is equal to V prime. That's exactly the enumeration algorithm. I first compute to each environment or each trace what is the probability, and then I gather everything. Okay, so you may have the feeling that we have done twice the same thing. Yes, that's true. That's exactly the theorem that we get. We have two presentations of the same semantics. One is computed with the sampling traces, and one is computing with stochastic matrices. Okay? But we get the same thing. Okay, and this is a theorem. This is a soundness theorem that says that for any statement S and any environment gamma and gamma prime, the probabilities that performing S starting from gamma, we get gamma prime is equal to the sum over all sampling traces of getting gamma prime with probability rho, where gamma prime rho is the semantics, sampling semantics of S performed from gamma sigma, starting with probability 1. This is a complicated statement of we have done twice the same thing. Okay? Okay, but it is really useful, these two ways of reasoning. So for instance, we want to prove that the left-hand side coin is the same thing as the left-hand side, right-hand side coin. How will you do that? Okay, I'll leave you think. Any idea? I give you a hint. You can use either the stochastic semantics or the sampling semantics. One is easier than the other one. I'm sure someone knows. If nobody tries, I will ask to experts. That means that's to seniors that are doing computation on their computers. Okay, Michele. Sorry?
I would use the kata semantics.
The stochastic semantics, okay. So on the left-hand side, what is the semantics of coin? So it doesn't take any input, so it starts from the empty environment. So what is the potential outcome? It's a Boolean. True or false, and it will give you true with probability 1/2 and false with probability 1/2. All right, I've done it. Okay, now for the other one. No input. What are the potential outputs? True and false. X can be bigger than n or less than n, so it will be it will also be true and false. So lambda b, and I will sum over all the potential values of my sample. So 1 to 2 to the n. So the probability of getting k is it's a uniform random int between 1 and 2 to the n, so it's 1 over 2n, and it's the multiplied by the expression is x bigger than n, and the output is b. Okay? So let's assume we compute coin true. Because it's a Bernoulli, we only need to know the bias. So we only need to know what is the probability of getting true. Okay, so it's the sum from k equal 1 to the n, to 2n, of delta true x is bigger than n. You see where I'm going? Okay, so I only half of the sum where x is bigger than n. So it's the sum. Right, thank you. K from n plus 1 to 2n, 1 over 2n multiplied by 1. It's 1/2, and now we know that the left-hand side program is equivalent to the right-hand side program to the semantics. 1 hour for this. Okay. Now for the second line, I have two programs, but I have only exchanged the order of sampling. Okay. What will you use as a semantics? Okay, the answer is easy. I am a teacher. I have an example of each one. Okay. Emmerich?
Some of all pairs in the sample space.
Oh, no. I want to use the sampling semantics. It's far more easy. Yes. Okay, so for the left-hand side, what is the sampling trace? So for x, I will have whatever value v, which is in the support of mu of x. And for the second one, for y, I will have whatever vx and v and v prime, which is in the support of mu of y. Okay? And now what is the sampling traces for the second one? Be careful, I will ask someone. Yes?
But it's the same as the first two samples. Y, first half is on y.
Oh, sorry. First I sample y, I get v prime, and then I sample x, and I get v. Okay? So that's the set of sampling traces. That's the set of sampling traces, and there is a bijection between them. Whatever is the order of the samples, you get the same trace. I can compute the swap to get a bijection between the two traces. So because I am summing over all the possible traces, if I have a bijection between the traces, then I get the same semantics. Okay? So the important thing is for any for this sampling trace and this sampling trace, I get the same result. Okay? So depending on what you want to prove, you will use one on the or the other semantics. And the important thing is they are the same.
Just a question to be sure. So if you had if the sample of the second one was parameterized like the first sample, how would that affect, if there was some effect of the two successive?
Oh, no effect here.
How would that affect the trace? Because it's not the case here, but how would that affect the trace?
So it won't affect the trace, it will affect the value, the environment at the end of the day. Okay, the traces are the same, but because you have an effect, they will give you the different expressions. Okay, that's why we consider no effect here to keep simple. Okay, so now for the end of this first session, we can move to a functional programming language. So some people will be more happy with that, I think. And okay, so I have a small, a simple syntax for BioPPL, which is like this. So the same types, but now I'm in function style, and I have a fixed point operator, recursive functions. The values are like this, and I again sample in the same thing. The semantics of deterministic expressions are the same, but for okay, I have also two sorts of semantics: the sampling semantics, which will affect this use the sampling trace, and then we will have the stochastic semantics. Okay, so now. Again, to each sample, we have a unique K. Okay. We have a unique K, and a trace sigma of sampling is again a map that associates to each key of the support, sample in the support of the sample distribution. Okay, so now what does it look like? We have an expression, and it will take an environment in which it is evaluated, a trace, and it will produce a value and a probability to get this value. Okay, so if the semantics of E in the environment gamma and the sampling trace sigma gives you V and rho, it means that the expression E evaluates to the value V, potentially with several steps of evaluation, and with probability rho. And it is denoted as this big step operational semantics. It's just to change a little bit between the formulation. Okay, so some rules. Let X equal sample in. First, I evaluate E1. It will produce mu in the environment gamma. Then I will look in my sampling trace what is the value associated to the key K. And now, if I evaluate E2 in gamma augmented with X takes the value V, not V1, V, and I evaluate it in my sampling trace what I have taken of k. Then I get value v2 rho. Then to do let x equals sample e1k in e2 will produce v2 with probability mu of v multiplied by rho. Okay. So now I can evaluate the associate to dice the semantics of this program, and it will, if you give me a sampling trace, so A is 2 and B is 5, then it will give you with 1/36. We always do the same thing, but in different style. Okay, so now the stochastic semantics. We will use, nice. We will use the subprobability distribution monad. Why? Because my expression will transform a non-environment into a subprobability distribution over the expressions. Okay? I evaluate my expression E in an environment gamma, and what do I get? A subprobability distribution of expression, and at the end of the day, after several steps, I will get a subprobability distribution over values of type E. Okay, so what I'm doing here is I will use the subprobability distribution monad on a countable set. And we'll denote it as D of X, and its structure is given for any, so it's a monad, so there is a unit and a bind, and the return is just the Dirac on X and X prime. And the bind is like this. You just perform the sum over all potential output value of X of nu, and you multiply the probability of getting X with the probability distribution Fx. F is a function from X to the probability distribution over Y. So you are, in a way, computing the mean of this probability distribution over the input X. So it's a kind of expected value. Okay, so now there we have the stochastic matrices as before, and there is a 1-1 correspondence between stochastic matrices and functions from X to the D of Y. That means that stochastic matrices are parameterized distribution, probability distribution. A stochastic matrix from X to Y is a probability distribution on Y, which is parameterized in X. Right. So I can define step by step the stochastic semantics rule. The step will take an expression E in my language, lambda p, and an environment gamma, and it will produce a subprobability distribution over pairs of expression and environment. So when I evaluate an expression in an environment, I get a new environment, a probability distribution over new environments and resulting expressions. So for instance, if I sample a one and I store the result in X to use it in E2, what I will get is the sum over all potential output values of mu, the probability distribution. I will multiply the probability of getting V by the fact that the Dirac that will be equal to 1 only on expression E2 evaluated in the context gamma, in which I have associated V to my variable X. Nearly the end. Okay, so now I have one step, but what I need is to perform any state to get a probability distribution over values. I don't want to be stuck in the middle of my evaluation. So what I will do is I will repeatedly do the step. I start from an expression and an environment. I get a probability distribution over expression and environment. I take the bind of my subprobabilistic monad, and I get a new probability distribution over environment and expressions and environment. And I do it again and again till I get only values. Okay? So because you are taking different probabilistic branches in your evaluation, that means that some branches may finish before the other ones. So when a branch is finalized, I stop here and I stay in the state. And the other one, I continue to evaluate them. This is the meaning of this execution. If E is not a value and N is equal to 0, then the probability of getting the probability distribution that I get after 0 step, starting from E gamma, is 0, because it's the probability of getting a value. Now, if E is a value, the probability of getting a value after n step, at least n steps of evaluation, is just the return on my expression E, which is a value. Now, if E is not a value, then I will perform a new step of execution and get a probability distribution, step E, and do the bind with execution of n-1 step. And because it is an increasing all what I get is the probability of getting a value. So it's a positive real, and it's more and more. It's bigger and bigger. I can take the sub and get the probability distribution of my expression E. Again, we have a bijection between the sampling semantics and the stochastic semantics. If you sum over all possible samples, the sampling semantics, you will get the stochastic semantics. Okay, so I think I will stop here. I have 5 minutes. Do you want to make this example, or do you want to make a bigger break? Who wants to do this example? Oh, at least 2 people. You are nice. We can stop here, perhaps.